Hi, my name is Paul Niyonkuru. I am a PhD student in the physics department. Today, I'll be talking about exploring molecular aggregation of emissive gas in phosphorescent light-emitting diodes. I would like to start with a short introduction of organic semiconductors. Why do we care about them? Organic semiconductors are cheap to make. Their fabrication temperatures are low. They can have flexible design that are compatible with plastic, and they make higher quality displays. They get their semiconducting properties from the ability of carbon atom to undergo sp2 hybridization. This is the mixing of 1s and 2p atomic orbitals to form 3 hybrid and 1 2p atomic orbitals. Once a carbon atom has undergone sp2 hybridization, 2 of them can bond to form molecular orbitals, pi bond and sigma bond by the overlap of the hybrid orbitals and p orbitals. And the semiconducting properties comes from the weak splitting between the bonding pi and the anti-bonding pi orbital, also known as highest occupied molecular orbital and lowest unoccupied molecular orbital. There are many types of organic semiconducting molecules, which is usually divided into biggest categories, being small molecules and polymers. And the diversity in this field allows band gap engineering. 2 key concepts to keep in mind in this presentation is the concept of polaron and exciton. They come from the charge carrier wave function being localized in amorphous material. A polaron is a charge carrier and the deformed molecule on which it is localized, while an exciton is just a coulombically bound state of an electron and hole located on the same molecule. Here is a basic layout of an OLED device where you have an electron transport layer and a hole transport layer. You have an electron blocking layer, hole blocking layer, and you have an emissive layer in which you want your charge carrier to meet and get confined and create excitons that are going to decay down, emitting photons. I'll be focusing on just the morphology of this emissive layer. So during an electronic excitation, spin statistics dictates that 24% of the formed excitons are singlets, while 75% of them are triplets. And the triplets excitons transition to the ground states are forbidden. Consequently, with fluorescence, you only have 24%. You can only get 24% efficiency. But with phosphorescence, now triplets are also able to decay down relatively. Consequently, you get 100% quantum efficiency, internal quantum efficiency. Phosphorescence is enabled by spin orbit coupling, which is basically adding some single character to the triplet states, hence allowing them to transition down to the ground state radiatively. We use transition metal complexes based phosphorescent dopant in phosphorescent material devices because they have strong spin orbit coupling. And the way we do this, we have a host of fluorescent material in which we dope about 10 to 15% of these phosphorescent dopants. And you want to make sure that the energies of these phosphorescent dopants are inside the host energies so that you can transfer all your excitons on the gas molecules where they're going to decay down through phosphorescence. Although theoretically speaking, the internal quantum efficiency of the device should be 100%, we see we see a roll-off as we go to higher luminance or a higher injection of charge carriers. This is due to two big mechanisms, at least as we understand today, one being the triplet annihilation. This is basically when you have two near molecules in the triplet excited states, one transfer its energy non-radiatively to the other one, and they gets excited to a higher triplet energy, which decays down through vibrational modes. The key concept being that you start with two excitations and you end up with one excitation. So you've lost one possible photon that would have been produced. Another one being the triplet quenching. This is almost the same, except that you start with one exciton, one excitation, and one charge polaron, and you end up with a ground state and a polaron. But in this talk, I'll just be focusing on this triplet annihilation. So we start with simulations of morphology to see how this TTA mechanism depends on the morphology. So I simulate three extreme cases, one being the inhibited. And here you make sure that no dopant has a nearest neighbor being another dopant. In the random case, I put dopants inside the emissive layer randomly, so the possibility of having dopants being nearest neighbors. And the linked morphology, it's an extreme case where each dopant has at least two nearest neighbors being dopants. I'm doing a kinetic Monte Carlo simulation of time-resolved photoluminescence. We observe that you get this TTA characterized by this initial curve in time-resolved photoluminescence being higher when you have linked dopants. This can be explained by a percolation path. Since you transferring all your exciton to the gas, which are confined inside the host energies, having percolation paths or linked gas allows your excitons be able to find each other and hence decay down through TTA. So after seeing this simulation, we tried this on actual devices. We create them through vapor deposition. This is an example of a device, physical device. And we see that we try to increase the number of nearest neighbors in actual devices by increasing the concentrations of dopants inside the host matrix. And you see that at high concentrations, you get more TTA, and this happens on, doesn't matter which host material you use. So we try to see those aggregation using STEM, counting on the difference between iridium mass being the core atom of the gas molecules, and the background molecules being just organics. And we see that the heavy molecules are able to show here with using TVM images. Another simulation we do is time of flight. So if we have these clusters, we'd expect most of the charge carriers to go through this path. And the simulation shows, so when you do a single device, a single carrier device, you see most of your charges being concentrated in one area. And we do actual experiments using only devices, and you're using conductive atomic force microscopy. We are able to see that you have a background in which you don't have high currents and some clusters in which you have high currents. And this is not doing a simple analysis. You see that these clusters are not correlated to the actual topology of the device. So supporting work we are now doing, we're using atom probe tomography to try to see the 3D map of these clusters. In a summary, we DTM imaging based on mass difference between guests and hosts. We use kinetic Monte Carlo to guide our intuition in TRPL charge carrier transport, and we also do AFM to study currents conduction in these clusters. Thank you.